pleasure for us to have Eva Darulova visit us from NPI, Saarbrücken. John and I have known her in our verification circles. She wrote a very influential paper on floating point correctness analysis and actually a compiler that will give you guarantees. And a lot of USS Propagation 20, whatever, 14. And then many influential papers since then. She's very interested in how to compute with the exact results expected. So she's touring the country and loved Salt Lake City, the tour we had. But anyway, hang around and there will be slots later if you want to talk to Eva. So, programming with uncertainties. Okay, take it away.
Thank you. Where should I stand?
That's
anywhere is fine.
Anywhere?
Yeah.
Okay, great. So thanks for the introduction. Just to mention, I'm right now at the Max Planck Institute for Software Systems. We also have a new logo, but I haven't found a version that would not collide with my picture. That's coming soon, but most of the work that I'm presenting here has been done while I did my PhD at EPFL with my advisor, Victor Kuchak. So let's start with an explanation of what I mean by the title, Programming with Numerical Uncertainties. So by programming, I mean that we want to implement a real-valued arithmetic function. So this is our program for now. So suppose we want to implement this approximation to sine. Now, just to note, we're not interested so much in the approximation error here to the sine function, but just the implementation. Now, the first question that you come across is, as you see on the question marks, which data type should you use? On paper, you would have actually written this in real numbers. Now, these obviously don't exist on your machine, so you have to come up with some data type. Now, there are various different choices. So you could choose standard single precision floating points, double precision floating points. Perhaps the precision is not enough, so you may have to go to double, double, and quad double, which are implemented in software. So that's why the runtime bars are a lot higher. Or perhaps this should run on an embedded system, so you would rather use fixed point arithmetic if you possibly can. So how do you make the decision? Obviously, the runtime is not the only thing that you care about. Usually, you also care about the absolute errors that are committed when using that data type. And as you see, the larger the data type is, roughly the smaller your errors are going to be. And you have a clear trade-off between accuracy and performance. So the goal of the work I'm presenting here is really to help the user navigate this trade-off. So really we do programming with numerical uncertainties. By this I mean round-off errors, but also possibly input uncertainties that may come from noisy sensors or something like this. And we want to do all this correctly. So we want to have some actual guarantees on the kind of numerical uncertainties that we get. And since we started this work, there's also another motivation that has come in from the approximate computing side, where the idea is really want to deliberately use approximations, maybe choose lower data types in order to increase the performance of our computations. Because very often we don't actually need the full, maybe 64-bit precision. So the outline of my talk, I'll first present a new programming model that we're proposing, and then I'll explain why. Then I'll go into more technical details of how we actually estimate these numerical uncertainties with different challenges that we came across. And then I'll finish briefly with how we actually want to improve the accuracy, not just check it. So first, the new programming model. So until now, people would write some floating point, perhaps precision code, and then run some analyzer on it. And we found that a little bit unsatisfying. So instead, we're proposing a real valued language, because this is what you ultimately would have on paper. But this is not enough to actually determine anything about what you really want to compute. So we also require the user to provide a specification that bounds the possible inputs that you can have, and potentially also input errors. So these could be the ones from noisy sensors. And then the user can also specify the maximum error that can be tolerated. Now, all these errors are absolute errors. I don't know of anyone who can really statically reason about relative errors. Hopefully, in a few years, we're going to have that too. So why do we want this real valued spec? So first, as I mentioned before, this is really what you would write on paper, what you really mean when you write down the function yourself. This is also what you may have proven correct, so proven correct with respect to some other properties, because reasoning is usually easier over the reals than the very complicated and unintuitive floating points or fixed points. It also provides us an actual baseline against which we actually compute the errors, which is explicit and not implicit as in many other tools. And in the future, this would also allow sound compiler optimizations. For instance, you may reorder the computation as long as the specification is satisfied. If you would write this in the floating point semantics, then rewriting is not okay because you're actually changing the meaning. So once you have written such specification, our very fine compiler, which I call Rosa, comes in. It's going to take that and it's going to pick a data type for you that satisfies the specification. Either floating points, and will print the program for you, but that really just means replacing the real type with the name of the data type. Or it can also generate the fixed point arithmetic code for you. How many people don't know fixed point arithmetic? Okay, so it's sort of like floating points, except that you don't require a floating point unit, so it can be implemented just with regular integers. But this also means you have to do some extra work at compile time, so that's why this code looks so complicated. So really these bit shift operations are the shift operations that the floating point unit would do for you dynamically, but you have to specify it statically. So there's some more compilation effort involved. You're welcome to try the tool. It's a prototype, so be nice to it, but at this point it should work reasonably well.
So your compiler does the shifting and all the other?
Yes, that's all done fully automatically, and that falls out of the analysis that we did.
It keeps the values in the range, that's cool.
Yes. So we're obviously not the first ones that look into numerical errors and numerical uncertainties. So just to put our work into context, a very short rundown of the state of the art. So if you want to reason about numerical errors, you can either be a numerical analyst. So this means you're going to be an expert that's going to sit down and do some proof by hand on paper. But most of the times, these kind of proofs are going to be asymptotic, and they're going to take a good bit of time. So you can also be into interactive theorem proving. This will alleviate some of the manual efforts, but it will require you to be an expert in both numerical analysis and theorem proving. But you can potentially prove very precise properties about your code. You could also just test your codes. So this is going to also scale to a lot bigger programs, but it won't give you really strong guarantees. So it really depends what you're looking for. Now our work is in static analysis. So our goal was to have something that's fully automated and sound. And then the challenge was to get reasonable accuracy. You could always get or compute an error of -infinity to infinity, which is going to be sound, fully automated, but completely useless. And this turned out to be actually more challenging than we thought initially. So the biggest part of this very fine compiler is really the quantification of the numerical errors. And the goal of that being static, sound, accurate, and fully automated. So let's start with something rather simple. So just loop-free branch from code, so just straight line arithmetic operations. And we want to compute the worst case absolute errors. For this, we need to bound the round of errors that are committed, and we also need to propagate these round of errors through the rest of the computation. Now it turns out that both of these actually depend on the ranges. So to summarize our static analysis at a high level, we just do a data flow analysis and at every node in the tree. We first compute real valued range. Then with this range, we can propagate the errors that have been accumulated previously. And with that range, we can compute a new round of error, and we continue. So first, we need to compute the real valued range. Now you may think this is actually fairly simple, so we could just use interval arithmetic. As you may know, intervals are okay, but as soon as you have correlations between variables, they're actually lost in the computation. So if you want to compute x minus x, you don't actually get 0, but something that's twice as large as you had before. An alternative would be a fine arithmetic, which represents your interval as a linear combination of noise terms. That's what these xi, epsilon i's are called. So this keeps track of the linear correlations. So the x minus x you can actually now compute to actually be 0, because the linear correlation here actually cancels out. However, if you have nonlinear operations, then these still have to be approximated. So when we found on some of our benchmarks that this just did not quite work as expected. So this jet engine benchmark we got from embedded systems, and when we tried to do the analysis, so just compute the real value ranges with interval arithmetic, turns out that the value T2 in our analysis has an interval that includes 0. And then later on when we try to divide by it, we get an interval of minus infinity to infinity. It turns out that this is actually a spurious error, so you don't actually get an division by 0 here. But intervals can capture that. A second case we found was, for instance, for this code, which is the textbook formula for computing the area of a triangle. But the formula only holds when you have a true triangle, so when 2 sides are bigger than a third. But that constraint cannot be really captured by interval or a fine arithmetic. So it turns out that for these kind of inputs, you then try to take the square root of a negative number, and again, this doesn't work. So really the challenge that we identified here was nonlinearity and correlations, and also these additional constraints. And this was trouble for the range estimation itself, but then also made the errors that we computed larger than necessary, if we could actually compute them at all. So our solution to this, after trying various different things of getting a smart defined arithmetic or something like this, which never worked, we took this fairly simple solution, which combines interval arithmetic with recent advances in SMT solvers. So in particular, we combine interval arithmetic with the NL-SAT solver inside Z3. So the procedure is very simple. You first compute an initial interval with interval arithmetic, and then use the SMT solver to do a binary search and try to narrow down the interval. So you get an initial interval, make it smaller, ask the Z3 solver, is this still sound or not? And the Z3 solver is either going to tell you yes, no, or I don't know. Turns out for the kind of benchmarks we had, this worked out better than expected. Has the advantage that the solver, because it uses cylindrical algebraic decomposition as a decision procedure, can take into account any correlations between variables, our additional constraints, and this allows us to also do the runtime checks for division by 0, overflows, and so on at runtime as part of the tool. Now obviously also the solver is really the bottleneck in the runtime, because every now and then it is going to time out, in which case we're going to always go back to the same interval arithmetic estimate. So some experiments that this actually works on some of our benchmarks. So we compared this to intervals and to a simulation of the range. So this gives us a fairly accurate underestimation of the true range. So this is normalized to 1 to the simulated 1, and the red one is our procedure, so you can see it's fairly close. Whereas intervals can overestimate the true range by a good bit, or don't compute any range at all.
So is the interval analysis done first and then Z3 brought in, but does the Z3 result then feedback into interval? Can they refine each other?
So we do this as a data flow analysis, so at every step we first compute the interval, then narrow it down, then compute the next interval. So it means that later on, when the expressions become more complex and Z3 fails, we already have a better estimate on the subtrees.
So the gist was whether the Z3 analysis would rule out certain sub-intervals that you can then plug back into interval, you do that.
Yeah.
So does it matter how often you make them talk to each other or feedback between the two?
So right now we really just first run intervals, then Z3, and then for the next sub-expression, first intervals and then Z3.
So why are relative errors a problem? Is it because of interval arithmetic?
So relative errors are a problem because in the expression where you try to compute relative errors, you want to divide by the expression.
So if it goes to 0?
Yes. So if that expression includes 0, which it actually does fairly often in practice, that's a problem. So today most tools will first compute the absolute error and then from that the relative error if it's possible. But that's more or less as good as just computing the absolute error.
Thanks.
Okay, so now that we have the ranges, we can go over to the errors. And for this I'll introduce some notation. So the F is the real values expression, X is the ideal input without any errors, F tilde is the finite precision variant of F, and X tilde is our actual inputs that are being fed to the computation. Now we don't compute the error as a total error like this, but we split it into two parts. The first part is really the propagation of the initial errors, and the second is capturing the round of errors that are committed during the computation. And the reason why we split this is at some point we realized that these are actually two different things, and we probably should compute them in two different ways. So the propagation of initial errors is a real valued property. So even if you could compute in real numbers, you would still magnify initial errors that you would have. Whereas the round of errors are really just a finite precision artifact. So we use derivatives for the first one and a fine arithmetic for the second one, and I'll go through them, but in the the other order. So let's start first with tracking round of errors. So we really, at every step in the computation, we want to capture what the round of errors are and somehow accumulate them. So for this we use affine arithmetic, and you can imagine that each of these noise terms are really just one of these round of errors that are committed somewhere in the computation. Now, even these you have to propagate through the rest of the expression. So the propagation here is just captured by the standard affine arithmetic rules. And then at each step, when you add a new error, you just add a new xi to the end of the computation. Now the magnitude of this is determined by the data type that you have. And this is essentially the only place where our method differs for the different data types. So if you come up with your new, completely different finite precision data type, as long as you can give me a method how to compute this new error, the rest just is applicable as well. So then the error propagation, as I said, this is a real valued property. So now we have really the difference between f's, but with different inputs, and we want to bound this. Now for a mathematician, it kind of screams Lipschitz continuity, and this is also what we use. So this is essentially a linear approximation of the difference. So essentially, you compute the derivative, and the intuition is the steeper the derivative, the more your initial errors are magnified. So these partial derivatives can be computed symbolically because we only have regular arithmetic, so this always works. And then we also want to bound them fully automatically. So for this we use the Z3 base range computation, and here actually the Z3 is critical because interval arithmetic just produces too big over approximation at this point. Okay, so now perhaps some people are confused because we have this derivative-based error propagation, but then the affine arithmetic does some propagation too. So why not just use affine arithmetic for everything? Now it turns out that affine arithmetic is fine as long as you have very small errors, something on the order of your round of errors of 10 to the minus 16 or something like this. As soon as these become larger, the over approximations also become much larger. Derivatives, however, are better when you have larger expressions, because then you're computing derivative of the entire expression, and you can take into account all of the correlations between variables at once. So that's where they come into have most use. So in practice, what we do, we first compute a round of errors for the expression of t, and these errors then become the input or initial errors for the expression t2. So then at the second step, the round of errors we first computed with affine arithmetic will be propagated with derivatives. So right now, we just use this whenever there's such a let statement. Currently don't generate them automatically. Obviously you could do that, that would be simple refactoring of the code. Any questions so far? Okay.
So once the initial errors are put in, it is basically derivative-based calculation then on. I mean, some of the later expressions also might induce a very large round off. So that also should be factored. I don't understand.
So when we start off with this expression,
Yeah.
we track the round of error that is committed in computing this expression with the fine arithmetic. And then you have some initial error essentially on t. Now, you also need to propagate that error through this expression. You could still use a fine arithmetic, but because then at some point these errors become larger and larger, once you define a variable like this, then from then on the error is propagated with derivatives. However, this expression also commits some round of errors, and that is tracked with the fine arithmetic.
Okay, so it's per depth flow chain as
Yes.
a link. Okay.
Okay, so we are obviously not the only ones. Surprisingly, floating point computation have garnered quite some interest. So the first tool really in the space was Fluctuate, which was more or less developed concurrently. They also chose a fine arithmetic to track errors, and they also found that at some point they weren't quite good enough. Their solution was to add some constraints on the fine terms and to use interval subdivision. F.T. Tyler, which some people here may know better than I do, chose a completely different way by posing the problem as an optimization problem and then using Taylor approximations to make the expressions small enough. Now that also works on transcendental functions, and I think you can also generate certificates. So Rosa currently does not handle transcendentals. We do have a student who's looking into that, but we'll see how far we get there. And then there's also the tool Real to Float, which takes a very similar approach to F.P. Taylor, but uses a different optimization procedure process. So comparison is exceptionally hard for this space. So first, I used to have tables in my presentations. That didn't quite work well because then you have these numbers that you have to compare. And it turns out that these numbers are very much dependent on how you formulate your benchmarks, what the inputs are. They're not very informative. Now graphs would be much better. Unfortunately, it's also very hard to plot them. So I think I'm just trying to skip this. I tried many different things in presentation. I never found a good way. So my personal conclusion is that for straight line codes, the differences are in general fairly small between the tools. The differences really come in when you have specific features in your benchmarks. So really the limits of where the tools start failing or start taking a lot of time are a bit different. So for us, our sort of bottleneck is clearly the SMT solver, which may time out unpredictably, especially for a bit more complicated examples. Fluctuate has predictable times, but the accuracy may deteriorate as your examples become larger. And at least in my experiments, F.P. Tyler could potentially have large running times when you had additional constraints. So I think it really depends on what you want to analyze, and you should just pick the right tool depending on some high-level information. Now, the comparison of running times I never quite liked because really these three tools are implemented in three different programming languages. In general, I think for most benchmarks, it's very comparable, I would say. Okay, so that was the nonlinearity, and the usual question I get at this point is, so what about branches? So suppose we had some very complicated expression and we wanted to approximate this, and we used, as I did, Mathematica that split out this approximation that essentially split the domain in two and used different expressions in different parts of the domain. So then you have a branch in your code, and then you should ask yourself, what happens when the real value computation takes one branch and the finite precision one the other because of numerical uncertainties? So this is especially important when our baseline is really the real valued one. So let's consider the very simple case of one if then else expression. And now let's consider that the real valued branch takes the if branch, real value computation, and then the finite precision one goes the other way, the else branch. So we actually split the errors again, but now in three pieces, not just two. So the first part is really the amplification of the initial errors in the if branch that is taken by the real value computation. Second part is just the real value difference between the branches with no errors. And the second one is the round-off that the finite precision computation performs on the else branch. And it turns out we actually have the tools to compute all of these three already. Now initially we tried to compute the error as a whole. We just created a huge constraint and fed this into our Z3 solver, which failed miserably. So the trick was really to try to separate this and make the individual chunks a little bit more easier to analyze. So again, the graphs. These times they're somewhat easier to explain. So there's now only two tools and the differences are fairly stark. So the absolute errors that we compute on our set of benchmarks, so we compare against Fluctuate, and the scale here is a log scale, so there are actually huge differences. So what Fluctuate really tries to do is this one big constraint, and that did not work for us and does not work that well for Fluctuate either. The flip side is that our tool takes significantly more time because of the three different pieces and the SMT solver. But it's still on the order, mostly on the order of seconds, so I think for sonic analysis this is still okay. Plus, I did not actually try to really debug the performance of the tool very much.
What is inside Fluctuate? I mean, this has been a problem for us. We get access to the code.
Well, so I also have just the binary, and I talked a little bit to the developers. So my intuition is it's a fine arithmetic with constraints on the affine terms. So essentially you have to express this divergence as a constraint on these affine terms.
Do they also have a lot of special rewrite like the KML and things?
I don't think so. I don't think so. And as far as I know, the tool is not being developed anymore. Okay, so then the next question always is what about loops? So loops are in general hard because when you have numerical errors such as round-off errors, they just keep growing with every iteration. So finding an absolute fixed point is usually not possible. So you could obviously unroll the loop. This usually does not scale, so either in our case the Z3 solver is going to fail or the errors become unacceptably inaccurate. So we found that for some loops we could actually express the error as a function of the number of iterations, and this allowed us to push the scalability a little bit further. But this only works for some loops. So I'll try to explain this. I'll need some notation for this, so bear with me. So by G, I'll denote a function that essentially propagates errors. So that's the derivative-based one. And sigma is a function that will compute round-off errors. So that would be the affine arithmetic-based one. And now we're interested in iterating our function n times. And we want to iterate both the finite precision one and the real valued one the same number of times. So we don't consider the case where one could take less number of iterations. So and then if you do some algebra on paper, you can come up, together with the separation of errors that we had before, you can come up with this expression which essentially says that, well, you take your input errors and propagate them m through the m iterations, and then you take the round of error from one iteration and propagate it through the rest. And just do this for all of the round of errors that you get, for all of the iterations. Now this is not yet very helpful because this essentially amounts to unrolling, because the G and the sigma could return different numbers for different iterations. However, if we could have a constant G and a constant sigma for our loop body, then this reduces to this very nice function, which is essentially just a function in the number of the iterations. This is again just some algebra on paper. So the case here are the Lipschitz bounds, the derivatives, and the sigma here is the constant round-off error for the loop body. So this works if we assume that the ranges for the variables that we iterate over stay bounded and fixed, and the user can actually provide us with them. So we tried very hard to actually prove that they stay bounded, but because, for instance, for this benchmark, which is simulating a pendulum, you would have to find a loop invariant that reasons about the energy of the system. It's turned out not to be that trivial, so that's a future challenge. So, but once we can assume that these ranges are bounded, then essentially we can just analyze the derivative once and for all for the loop body, do the same for the round-off, and then plug it into our closed form expression. And this actually scales to, in this case, for up to 500 loop iterations, whereas Fluctuate, that's doing unrolling, scales to about 50. Now, to be fair, the Rosa with the Z3 solver didn't scale to even 3 iterations in this case. Okay, so that concludes the section. Are there any questions so far? Okay, so really, as a summary, the key ideas in our work was the separation of the errors and a combination of fairly standard tools like interval and affine arithmetic with the advances in SMT.
So I have a question. So
Yeah.
would this work be applicable for Fixedpoint? Because some of the embedded system situations, much like pendulum, might arise in Fixedpoint arithmetic more.
Yes, so actually because we compute the ranges at every point, from this we can compute the fixed point formats. Right now we assume a fixed bit length for the entire program, but this could be, with some implementation efforts, could be relaxed.
That can help you synthesize code.
And with these ranges we can then automatically synthesize the codes, yes. Now we are not going to, well, we cannot guarantee that we synthesize the optimal fixed point code because of over approximations potentially, but we can guarantee that there's no overflow. Okay, so one thing I haven't mentioned so far, well, very briefly at the beginning, is that finite precision arithmetic is not associative. So when you change the order, then the errors change that you have. So in the previous work, we always assumed that the order that was written by the user was the order that will be actually executed on the machine. So for example, we could take a fixed point controller for which we can determine the true error approximately by simulation. And then if you just change the order of that sum, so it's really just the sum of terms, then suddenly the errors could become even double, twice as large as before. Now for embedded systems, this is troublesome because this affects the stability of the controller proportionally. So this is the pessimistic view. Now the optimistic view is that we can actually go the other way and try to exploit this non-associativity and reduce the round of errors statically. Now, one note in particular with respect to some related work. In this case, we do not actually aim to fix catastrophic cancellations. So catastrophic cancellations occurs in finite precision code when you try to subtract two numbers that are very close in magnitude, and effectively you're subtracting away all the significant digits. In all of our cases here, now obviously we would detect this catastrophic cancellation, but this improvement of error also applies when you don't have this bad case. So it's really like the common case that we're trying to optimize. So this was joint work with Indranil Saha and Rupak Majumdar at the time. So we quickly found that just enumerating all possible orders of computation wasn't feasible. We also found that you would think a dynamic programming approach could work, where you first try to optimize your sub-expressions. Unfortunately, you could reach a very large error at the top, so this doesn't work either. So we chose genetic programming as a search strategy together with our static analysis as the fitness function. So essentially, the smaller the error, the fitter the expression. The mutation operator was really just the standard mathematical properties like associativity and distributivity. We actually tried to use some crossover as well. This had, well, moderate success. Was a little bit tricky to implement because we were trying to have a semantics preserving operation there. But I think this is not quite important. Because in the subsequent work, we did not even bother with that at all.
Question here, did Herbie, they work at UW, did they have any strategies like genetic?
So they had a similar heuristic search, I guess. I think they called it hill climbing with some, but they had a lot of other stuff that was going into it, so it wasn't just the search strategy that was important. Okay, so when we're using the static analysis as a fitness function, there is one thing we should consider. Namely, so we're using it to essentially determine when we have two expressions, which one is better than the other. However, when the static analysis says expression 1 is better, it could be that it's because truly the true error is smaller, but it could also be just due to over-approximations. We've just computed a smaller error for that expression. So we did some empirical experiments to see whether we actually get the true best expression out of it. And here are some plots that try to show what's going on. So this was a 50 equivalent rewritings of a linear expression. And it's comparing the analyzed error against the simulated one. And you see that there is a very nice correspondence. So this essentially suggests when we have a linear expression, when the static analysis says the error is smaller, it's actually smaller. Now for nonlinear computations, there is some correlation, but it's not quite as perfect. Now that said, in our work, we really were interested in being able to prove the smallest error. So even if the true error is not, even if we found an expression that did not have the the true error being the smallest, we were still happy with it because, especially in embedded systems, ultimately you want to prove something. So even if the true error is smaller and you can't prove it, it's probably not very useful. So anyway, overall, we can provide pretty much any guarantees except that when we return an expression, the error bound that we return for that is actually sound. So in particular, the search is obviously incomplete. And the static analysis may not discriminate correctly. Now, if you tried to use a dynamic analysis, you would actually have exactly the same problem, except that you wouldn't be over-approximating the error, but under-approximating. So just some illustration how our genetic search works. So this is a plot over our population of expressions and the min, max, and average errors that they have over a number of generations, and as you can see, the population sort of moves towards a better expression, and this was across our experiments. Now, our initial experiments were done on fixed point expressions from the embedded systems domain, and here are some of our more challenging, bigger benchmarks. We could more or less improve the error by up to 70%, and the bigger the benchmarks were, the bigger the savings were. And as I said initially, this directly translates into better stability of the controller. But that wasn't my work, so I'm not going to talk about that too much. So we've also re-implemented this work in a successor to ROSA. So here I have some initial experiments on floating point arithmetic. So the same approach applies just as it did for fixed points to floating points. These benchmarks are linear, so you can see much higher error savings, so that's again on the order of 70–80%. Now these benchmarks, which are a little bit more mixed, are the nonlinear ones, but even there we're able to improve the errors. Now sometimes you see these dips below 0, so these are the true errors. So this is exactly the case where we were able to prove a smaller bound, but the true error was actually bigger. So we were, again, not the only ones. So there was some work in the abstract interpretation domain. Unfortunately, there's no real comparisons at this point, so I can only give you like the high-level points. So Mathieu Martel did a local search. There was some SMT-based synthesis, which unfortunately only worked for linear expressions, just by the limitation of the SMT solver. And most recently, there's a Herbie tool from UW that had a testing-based heuristic search. Now, in my understanding, the goal was somewhat different. So this was really the cancellation fixing, mostly. But again, we don't really have a fair comparison here. Okay, so that brings me to the end of my talk. So I hope I convinced you that quantifying numerical uncertainties is actually hard. Took the whole of the PhD and we're not done yet. But in the end, really, what worked for us was a combination of different techniques and advances in SMT that gave us some automated and I think fairly accurate results. But there's still a lot more work to be done. Thank you.
Some questions?
What I know is a library you use.
It's my own implementation. I tried for various different libraries at some point, but each of them had bugs which we found within days, and then
Yeah.
we just...
There we go.
Now, if you want to use mine, if you're willing to work with Scala, please feel free. You can also just copy the code and translate it into every language. I can't guarantee it's bug-free, but it's been used for a couple of years.
Right, does it support transcendental?
So my student's working on that.
Okay.
So maybe within 2 months, if everything goes well.
Everyone I found had bugs in it.
So I have an implementation which is not online, but I can send you a copy. But this was not implemented, so this was in a previous tool, which was implemented in floating points. So the current implementation is over rationals. But if it's helpful, I'm happy to send
I
it.
want to implement over rules.
Sorry?
Implement over rules
That's obviously an option, but we actually did it
with rationals.
so
With
the
floating points.
with floating points, but not going through intervals. Yes.
So I really like the approach of, you had early on, like the sign example of annotating at the function level, bounds and things. How sophisticated can annotations like that get, and how sophisticated could the compiler be? So like for the sign example again, maybe I can imagine someone is willing to tolerate a fairly large absolute error, but it's very important that the output sign is always between -1 and 1. So, if you get a sign more than one, subsequent calculations might blow up. Can I what might be nice as a programmer, describes the infinite series, and the compiler can figure out that, depending when you take an odd or even number of terms of it, you're always going to be either the error will always be either towards 0 or away from 0, and
Yeah, so I haven't talked about it too much. So right now, the kind of constraints we take into account are these box constraints, so upper and lower bounds. In principle, you can add any kind of arithmetic constraints. And also for the post condition, we actually can check that your result is within the ranges, because we actually do compute the ranges as part of our analysis.
Right.
Now, the constraints you put in could be as complicated as the solver can handle, because ultimately we can just feed this into a solver.
Okay. So in conjunction with the genetic mutator, do you think it's a sensible thing to do to kind of have a high-level description of the precise result, and then the mutator not only reorders for associativity and distributivity and so on, but actually changes what's being computed, eliminates terms or whatever, and still checks against the...
Sure, but this is a lot more complicated
Yeah,
than that. And I guess I would rather try to separate these things, so perhaps try to do the high-level approximations first, and then try to optimize the code that you get out at the end. But then you also need other verification techniques. So not just the random error, but then you have to also take into account the approximation error.
Right. Thanks.
Thank you.
There are some who want to adopt infinite precision arithmetic. What would that do to your algorithms?
So our assumption is that the kind of codes that are put into our tool are robust with respect to some noise, so that finite precision is actually appropriate. Now there are some codes like geometric algorithms where you have to decide whether a point is left or right on a line. This is not applicable to that. It's just not appropriate. So I think it really depends on the application. If you have something like embedded systems, it's probably not going to be feasible to use infinite precision. It's just going to be too slow. It's going to take too much energy.
I should point out that the questioner is from the other side of CS that we don't usually communicate with. He's into numerical analysis and sync functions. I think this is a problem that I face in this domain, that computer scientists are entering this domain without too much data knowledge, including me. And so, what communities have you found more resonance with? Is it embedded or automotive? Or, I mean, where do you think you will find the best traction?
So for now, probably embedded, because you can also find interesting programs that are not too large, because scalability is still an issue. So for a start, that's probably the biggest effort. And those communities usually care about performance and errors.
I should also point out that the community has benefited a lot from their groups, especially Eva's benchmarks. If you look around, the benchmarks we use in our FP tail paper, the FP30, they're all cut and paste of their benchmarks with some more added. So thanks for that. But we should grow the benchmark suite. This is another thing that we can offer to you.
But to be fair, I also just pulled them from some random physics textbook.
It's okay.
They're
Somebody
real
has to
in
do
that sense. Apparently physicists care about it.
All right. Well, if there are no more questions, feel free to ask later, or let's thank the speaker now.